So welcome to this MEOW seminar, and Anastasia Sofronova will tell us about lower bounds beyond DNF-Xor.
Thank you. Thank you. So I hope you can hear me all right because I'm still a bit sick. So welcome to the reality show Delirious Lower Bounds. This is joint work with Artur and Dmitry Sokolov. And we'll be talking about some circuit lower bounds for circuits with parity gates. I think some of you might have heard some parts of this talk, but I guess that's fine because this will escalate quickly. Yes. Right, but let's start slow. So, circuits. What are circuits? Basically, you have some underlying graph of the computation. It's directed acyclic. You have some Boolean operation in the nodes. And this represents a computation of some Boolean function. Like you can just evaluate nodes in topological order and compute a function. And let's take a look at the restricted model for circuits. It's constant depth circuits or AC0 circuits, where your underlying graph of the computation is essentially just a tree of constant depth. The fanning of all of these things is unbounded, and you have interchanging layers of ors and ands and so on. The negations are at the bottoms with the variables, so you have like literals at the bottom, and the top gate computes your function. Right. So this is not a very strong model, right? So it's quite weak. It cannot even compute parity efficiently, and the kind of a lower bound that you get for parity is 2 to the n to the 1 over d minus 1 or something like that for depth d. And this is kind of the best lower bound that you can get, that we know in this model so far. While we would really like to know something without this epsilon here, like some true exponential lower bounds. I will explain why in a moment. But okay, so we have the parity function, and it's exponentially hard for AC0 circuits. And you can prove this by this random restriction or switching lemma technique, which is essentially you apply a random restriction to the variables of your function, of your circuit. And two last layers, they just collide into one. And you repeat this several times, and your circuit becomes a trivial one. But the parity function is very stable under restrictions, right? You can restrict almost everything, it will still be parity. So that's kind of the source of its hardness, and this is kind of a model example for this random restriction, aka switching lemma. So like that, this is why it's hard. Right. And about polynomial approximation, we will have a better context to talk about in just a couple of slides. Okay. Right. Lower bounds without the epsilon limit here. Why are we interested in this? Basically, one of the reasons is that, well, for general circuits, when you don't have a restriction on the underlying graph, except that it's acyclic, the best lower bound that you can get is linear with some embarrassingly small constant. While we would like, well, something exponential preferably, right? And so it turns out that any kind of circuit, you can just squish into a depth 3 one with some blow up in size. But the parameters are such that if you would get a truly exponential lower bound for a depth 3 circuit, like of the form 2 to the omega of n, you would get a super polynomial lower bound for general circuits. And this is like beyond our wildest dreams for now. So true exponential lower bounds for this would be great, but it seems like switching lemma cannot give us that, right? And let me just keep a list of things that current techniques seemingly cannot give us. You had a question?
Right. So this squishing that you described, can you also say that, like, could you also get maybe from not from a truly exponential lower bound depth circuit, but for some very strong ones, if you get what would you need for a superlinear lower bound circuit?
I'm actually not sure what are the parameters. I would need to check. I would need to check the paper.
Okay.
But yeah, I mean this whole thing with the epsilon being 1 over d-1, this is like a barrier that our techniques cannot reach right now. So even like getting better than square root n in the exponent for depth-free circuits would be already very good, just because we cannot do that at the moment. So that's like some psychological barrier, I guess. Okay, so let me keep this list of the questions that are beyond what we can do right now. And I will make a point at some point. You will see where I'm getting at with this list. Let's move on to another circuit class, which is stronger than just AC0. So I mentioned that, like we know the parity function is like reasonably hard for AC0. What happens if we try to add to AC0 some functions that are hard in this model? Well, we get a model that's like has more computational power, and it's that much harder to prove lower bounds. So, okay, suppose we allow our circuit to use also parity gates, or more generally mod M gates, where mod M gate just tells you if the sum of the variables that feed in of the gates that feed into it is 0 mod M, something like that. So now this model can compute parity, for example, and you can get some lower bounds using this polynomial approximation technique that I mentioned for M that is a power of a prime. And there is a certain reason why power of a prime. Basically, because what is this method? From a small size, small depth circuit, you can get a polynomial that approximates your function of a small degree over some field. And like you need some field to work in for this. And you can only have a field for that characteristic. So for example, when M is not a power of prime, we don't really know what to do. And the minimal example of this regime is, well, 6, right? So if you're allowed to use gates mod 6, not very clear what happens. Right. Okay. So let me just add this one to the list too, AC06. We don't know what to do with that. But even if it's not just arbitrary mod M gates, let's just stick to the parity gates at the moment, right? Let me say that I only allow my circuit to use parity gates. And moreover, I allow my circuit to use parity gates only at the bottom layer, just before the literals, only there. So you get a model that's called AC0 composed with XOR, and it already computes parity, right? And here's a conjecture that IP inner product should be hard in this model. This is actually connected to the problems of finding rigid matrices. It's not a trivial connection. It's like connected with like correlation with sparse polynomials or something like that. I'm not going to be telling about this in many details because this is like more involved than I would like to make this. But this is like a reference if you want to know more about this. I think this paper is called On the Special Case of Rigidity. Right. So what's the catch with this conjecture? IP is a small degree polynomial. And while for circuits with parity gates, polynomial approximation, the Rostov-Smolensky method works. It works for functions that cannot be approximated by small degree polynomials. But if you start from a small degree polynomial, polynomial approximation doesn't get you anywhere. Moreover, IP is computable if you allow to use XOR gates not only at the bottom, right? So the slabber bound, if it's true, it should be very specific for this model. And we don't actually know much about hardness of IP in this circuit subclass. We know worst case slabber bounds for DNF-Xor. That's the circuit here in the picture, or and of XOR. The best ones are in this paper by Korn and Shinkar. Before that, they were ones by Yukno. They're truly exponential, but worst case. So even then we move like to average case DNF-Xor. We don't know correlation bounds for this class. So we don't know any strong average case slabber bounds for DNF-Xor. So let me add this to the list too, right? Okay, but there's more still that I want to talk about, because I care about proof complexity, and I believe that most of you do too, right? Okay, so let's make this detour why we as proof complexity theorists should care about circuits and circuit slabber bounds. So proof complexity. So you have a formula phi, which is unsatisfiable. It's a conjunction of clauses, and we're interested in the question if we can efficiently prove its unsatisfiability, where efficiently means in polynomial size, and proof is something that can be efficiently checked efficiently in polynomial time. So like we would like to say that there are formulas for which we cannot produce efficient proofs, right? And often proofs that we look at in proof complexity, they look like this. So it's some sequence of lines where the last line just reaches contradiction. Like you assume that the formula is satisfiable, you do some deduction steps, and you reach a contradiction in the end. And often these lines of your proof, they are some kind of small depth circuits. For example, if you just allow your proof to use clauses, circuits of depth 1, just the junction, you get a resolution proof system. Right, and you also deduce the lines in this proof from your previous ones via some syntactic rule, usually, that can be efficiently verified by a computer. Okay, let me proceed to some examples of proof systems that work in this way. So here's the first example, AC0 Frege, where the lines of your proof are AC0 circuits. And miraculously, the lower bounds in the systems are obtained by switching them the same way that the lower bounds for AC0 circuits were obtained, right? So we had some technique for circuit lower bounds, and people just took it and transferred it to proof complexity. Well, why don't we do the same for polynomial approximation? Well, that didn't turn out so well. We have a proof system that's AC0P Frege, where lines have AC0P circuits, and we don't know any lower bounds in it. So it was like, it turned out very challenging to adopt polynomial approximation for proof complexity needs. There's some intuition behind this. I suppose because like unsatisfiability is just not a very robust concept, right? And when you're trying to approximate something with polynomials, you introduce an error inevitably. So that just doesn't make the match well, I suppose. But as an attempt to adopt polynomial approximation for proof complexity needs, they were introduced algebraic proof systems, and they are very widely studied today, and that's good. That's good. Let me also give you another example. Ras-Lean or Ras-Plus proof system, where the lines of your proof are the circuits of this form, or of linear forms. So as of now, lower bounds are known only for like different versions of regular version of the system. And yeah, I guess that's another point for studying the circuits with parity gates and understanding their power more precisely. I'm adding this one to the list as well, and I think this is quite enough. So these are just like number of open problems that are beyond current techniques for the sole reason that so there is a certain gap between things for which current techniques work and things for which we would like to prove lower bounds. And these questions are hard for the exact reasons that they lie in this gap, which is honestly everything a good open question should aspire to. Right? But this is why they're hard. Okay. I hope this was illustrative enough. And now I would like to talk about other circuit lower bound technique that we've been at with our group for quite some time. And this is called a top-down lower bounds. Let me just do a general sketch of how these things look like. This is like a purely combinatorial approach to this circuit lower bound stuff. Okay, suppose you have a circuit and you have a function. And you want to prove that this function is hard for circuits like certain depth. Okay, suppose you have a small depth, small size circuit. Well, then it should not compute this function, right? Then the circuit should make an error somewhere. Well, let's find this error. Okay, suppose it actually did compute the function, right? Then let's say the top gate was OR gate. Let me move to a subcircuit here, like this subcircuit. I'm telling you that this should still compute then all the zeros of the function because OR gate works this way. We should compute correctly all zeros in all the subcircuits. And also subcircuits of this gate give you a covering of one input. Again, for the OR gates to be computing the function correctly. So when I move to the subcircuit, I have this picture. I have some set of one inputs and all of the zero inputs. Okay. This is just a circuit of depth 3. So let me stop here and say that, okay, if my big circuit, my circuit of depth 3 made an error, then one of the subcircuits should make an error. This subcircuit is actually a CNF now, a subcircuit of depth 2. And I'm saying that I can bound the fan-in of this gate to K, where K is something like unto the epsilon. So I have a CNF of bounded width, and I want to argue that it makes an error on sets that look like this. And this error is a special point called K limit. So let's assume for a moment that this CNF actually computes all this stuff as it claims to, right? What does this mean? It means that the zeros of this KCNF cover this set of zeros, and the ones of this KCNF cover this set of ones. So what are the zeros of the KCNF? It's the union of zeros of the clauses, right? So, okay. And what are the zeros of one particular clause? Like, what do I need to do to falsify this clause? I need to set all the variables that appear here to a certain values. It's K variables that I'm setting to some values. So this is a subcube. So suppose this is like a subcube that corresponds to the zeros of the first clause. And this is a subcube that corresponds to the zeros of the second clause, and so on and so on. And I'm just covering with these clauses all of my space of ones. This is how it looks like. So if I'm able to do this, cover all the space of zeros without touching the space of ones, then I will separate the sets of inputs with KCNF. So now I want to argue that this is, by the way, along the lines of Kostyuk-Kudman top-down lower bounds for depth-free circuits. Right. So I want to argue that I cannot do this. What can I say to argue this? I'm saying that there is a point here such that when I try to cover it with some subcube of codimension K, I will inevitably hit my set of ones here. So there is this special point such that whatever subcube for dimension K I pick such that it lies in it, I will hit this set as well. And this is a K. And let me do a close-up of this point. Because picking a subcube of codimension K, what does this mean? I'm fixing the value of K variables here. So here's my point. I'm looking at any K bits that I have here. Then I'm looking at the set. And here's another point, but in the set that locally looks the same. So it lies in the same subcube. We have the same values in the same indices. I'm trying to take another subcube, right? So I'm looking at some other indices, K indices. I'm looking at the values here, and I see the same picture. I can find some point in the set such that it locally looks like this. So that's the K limit. Right. But what about circuits with parity gates? I promised you circuits with parity gates, right? Specifically, the subclasses of this class, AC0 composed with XOR. See, the thing is, all these top-down techniques there so far work until depth-4. And the main example for which they work is parity. And this model, it can compute parity, so this is kind of a challenge. But okay. Let me just try to analogously define the same things for starters, right? Suppose I have a depth-free circuit composed with XOR. So I have 3 layers here and then an additional layer of parity gates. What changes for us here? Well, when I do my first step down the circuit, I still get some subset of ones here, all of the zeros here. But now the subcircuit here is not a K-CNF, K-parity CNF. And these are not clauses anymore, but clauses of linear forms, right? So K-limit was able to fool K-CNFs. So it was able to fool subcubes of codimension K. Now I want to find a point that is able to fool affine subspaces of codimension K. Because what is the zero of this thing? You need to negate all of these linear equations. So that's a conjunction of linear forms. This is an affine subspace. So I need something like this. I need to find a point such that when I try to cover it with some affine subspace of codimension K, I hit my set of points. That's the idea. Right. But that seems like a very difficult problem actually, because as I mentioned, this depth-free composed with Xor lower bounds, this is not this is like beyond our reach right now for IP and like for small degree polynomials and for things like that. So, but what can we gain when we're phrasing the problem in this top-down language? We can see what kind of intermediate problems are there and what are overall the challenges. Like, why is this problem hard? Maybe this will give us some insight about this. Okay. And also, as I mentioned previously, the main example for which this top-down approach worked is parity function. Now, when you are taking even a very restricted subclass of AC0 plus parity, you need to allow it to compute parity. Otherwise, it's just silly. Sorry.
Can I ask a question?
Mhm.
Maybe I missed something because it's, what if my function has only one zero input and everything else is one input? Then that point is a k-limit, assuming k is not n.
Wait, if your function has only one,
1 0 is zero on one point.
when it should be very easy to compute, right?
Yes.
Then it shouldn't have a k-limit.
Why is
You
that?
not necessarily have. Oh, I'm sorry. Maybe all the k-limits of the set lie in the set. That could happen. If you take something that is computable by KCNF,
I don't think that example is connected by at least the maybe by n maximum.
what's the example again?
The function that is one except on point or zero. Or function. Yeah, and then why is not that point of k-limit? Any codimension k subspace containing that point must contain something else.
Yeah, okay. This is so this is a little bit of non-symmetric notion, right? So I think in one direction, that really depends on where your function is zero and when it is one, right? Because you can write down short formula, I suppose, in one direction. Like you can write down that for example, every point that you accept is different from this one chosen one in some coordinate. What would that be? A clause or a term? But you're right. If you pick one point in the Boolean cube, it will be a k-limit with respect to everything else. But the other way, it's not true. Did I answer your question?
Yes.
Okay, cool. Very sorry. Okay. Back to circuits with parity gates. What are our candidates for lower bound if it's not parity? Well, my favorite one is middle slice. It's the function that is one on the strings that have half of the Hamming weight. Then our favorite low degree polynomial IP. and affine disperser, but it's a bit tricky because you can actually compute some kind of affine disperser in depth 3 plus XOR, I think. I think yes, but we'll be considering a little bit of a bigger model. Let's start with this model. I think it was the place where I read about this is this paper by Juan Ivanov and Viola. I don't know if it's mentioned somewhere else. If you know, tell me, please. Here, instead of just allowing to use arbitrary XOR gates at the bottom of the circuit, you fix arbitrary affine map. So you just change the coordinates somehow. It looks somewhat like this. So this is the function you want to compute. You apply the change of coordinates. Now this is the function you want to compute. And you can apply AC0 circuits on top of that. So this model can already compute parity. So this is already a challenge to prove some kind of top-down lower bound for this. So let's consider depth 3 basis model. And in our top-down terms, what we need to prove a lower bound here is to find a k-limit with respect to arbitrary change of coordinates. So here's how this goes. You pick a function for which you want to prove a lower bound. Then the circuit tells you the change of coordinates. Then you do your top-down strategy knowing the coordinates that you're playing against. So like, in particular, this first step, which subcircuit you pick on the first step, it can depend on the change of coordinates here. And then you find a k-limit in this new coordinates here. This also knowing the new coordinates that you're having here. But we can actually do more. We can consider this kind of model or composed with CNF basis, where the difference is that the first step does not depend on this new basis. So you pick your hard function. Then a circuit tries to compute it. And you don't know yet what's happening at the bottom with the parities. You make your first step. You pick a subcircuit, which corresponds to picking a subset of ones here. And then the circuit tells you the affine map that it's using, the change of basis. And then you can pick your point, your k-parity limit, with respect to these new coordinates. And this point can depend on the change of coordinates. It's a little bit, it might be a little bit hard to understand right now. But the point is that this kind of circuits, they can actually use exponential number of parities. But in each subcircuit, that is k parity CNF, it's only n different parities. But these can be different across different subcircuits. So to get a genuine depth-free composed XOR lower bound, you would need to change places of last two quantifiers. So you would need to be able to find a k-parity limit that works for any basis, right? So far, like this step is independent of basis, this is dependent on basis. If you would find a way to find a k-parity limit that works for different bases, that would be a genuine depth-free composed XOR lower bound. But what's good about this model is that, first of all, it's strictly stronger than DNF-Xor. So it contains both DNF-Xor and depth-free AC0. And since these two are incomparable, you can do both. You can do both depth-free AC0 and DNF-Xor. The proof the lower bound for middle slice and for the affine disperser is some variant of unpredictability from Meyer and Victorson. I will tell you about it in the second part, I suppose. And yes, the challenge for this model is to be able to find this point, like with respect to this set. You need to produce some kind of K-parish limit for any affine map. But again, these points might be different for different affine maps. And if you find a way to smash them all into one, that would be just great. Okay, how much time do I have? Actually, okay. So we have time to talk a bit about open questions. Okay. So I mentioned several times that the ultimate goal, like for this, like, okay, not the ultimate goal, but like a big step towards some circuit lower bounds would be to able to find these K-parity limits for different bases. Okay, let's start with just a point that works for two bases. This, so this is like a top-down formulation of a problem that we want to solve. Find the K-limit that works for two different changes of coordinates. In terms of computational models, this corresponds to that kind of computational model. Two DNF composed with CNF bases. A bit of a mouthful, but it makes sense when you look at it from the top-down perspective. And then, let me go over this not exactly in order. Okay, the unpredictability thing that I mentioned. It produces a K-limit as kind of a local perturbation of the set. So you have the set for which you want to produce a K-limit. You take some point of the set, you make some local changes, you get a K-limit. The thing is, this shouldn't be always the case. There should be some K-limits that we are not able to produce this way. Again, I will try to explain this in the second part of the talk, but it would be very nice to get some other ways to produce K-limits that work somewhat on a global scale. And then how does this model that we get compare with average case DNF-Xor? That would be very nice to know because so at some point, I thought that this model here should contain average case DNF-Xor with like 1/2 error or something like this. Now I'm not actually sure, but yes, I'm pretty sure that we should be able to put this class into something that's into some class that are describable in a good way in this top-down perspective. There is also a thing about K-limits is that they are complete. So top-down technique is complete for AC0. Basically, what it means is that if there is a lower bound, you should be able to find your way down the circuit up to depth 2, and then to produce a K-limit. We don't actually know if this is true for K-parity limits. But in some way, we can change the definition a bit such that it will be true. Again, we'll explain it in the second part. Yep. That's it, I think. Yes, thank you.
Okay, any questions?
So I think I missed your fourth question there. How do these two compare on average case? So yeah, what's the intuition there? What do you expect?
So here's the intuition. I think I need a little bit of a word. So like, what is average case? DNF-Xor. Can you see me over there in camera? Is this
Not terribly well, no.
okay?
I don't know if you can switch on.
You can switch on the lights there.
Mhm.
Get a tape.
Go ahead and improve it.
Yes. It's
Okay. So,
perfect. Okay.
so you have your function that you want to compute zeros, ones, and everything. So you don't see anything.
Yeah, no,
Okay.
no, it's fine.
Right. So okay. What's like average case? You can lose some part of your inputs to error, right? So in terms of top down, this is like, suppose you lose like half of your zeros. Okay. So I don't know if they're not there anymore.
Yeah, well, yeah.
Okay.
That's
So
not
suppose I want to prove some lower bound for average case DNF-Xor. Maybe not a strong correlation, but just any average case lower bound. That's top down. I just want to adopt the technique or whatever. Okay. What's my DNF? It's or and right. So in this sense, the error in ones, you can forget about it right away because when you do it's also easier to think in terms of this top-down technique because when you do the first step here, you kind of forget about part of your ones immediately. So if there was an error, just some more collateral damage. That's right. So the meaningful error is 1 in zeros. If you start from this repeatedly, where the top gate is 4, right? Okay. So this is like already depth 2 plus parity. So to prove a lower bound, you would need to like forget about half your zeros and then find a k-limit. Let me say in which side for which. I think here. For this side. Yes. So in some sense, when you try to prove a top-down lower bound for this 2DNF CNF basis thing, what happens is that you first split the set of ones, then you again split the set of zeros in half, and then you find the k-limit. So this should be kind of a stronger thing because you are able to forget half of your zeros already after the first step. So this is kind of another order of the quantifiers.
Okay.
I wasn't able to prove formally that you can put one model into the other, but I have a strong sense that if you're able to prove a lower bound for this class, you should be able to do something for these two analogously.
Pictorially, what is 2-DNF for
Right.
DNF dash basis?
Right. And you want to erase all this?
I'm not very prepared for the blackboard.
I think there's some eraser behind that.
Okay. So right to DNF. That's a 2 DNF, right? And then it's composed with DNF bases. So it's and again, or and then XOR. But in these subcircuits, the affine transformation is fixed. So what you do here is here in this gate, you pick between two affine transformations or something. This is why it kind of corresponds to being able to find a K-limit that works for two bases. You do the first step. And this is like different ones that you get, different zeros. And then the words find a K-limit that works for two bases is basically find a K-limit that works for both of these subcircuits that can use different affine transformations.
So what's the time for the second half?
Yes, for the second half, I want to tell you a bit more about K-limits and K-parity limits and this like completeness thingy. I want to expand a little bit on all these open questions. I will tell you a bit about the proof for the middle slides. And I want to give more details to this third thing. I will explain how to find the K-limit with this unpredictability. And we'll see that it is indeed some local change. And I want to present this open question more concretely. Like, what's the example of the set for which we should have a K-limit that we are not able to find as a local perturbation?
Okay. So thanks again.
So we are back after the break for the technical part on the board with Anastasia. So without further ado, please.
Yes. So I talked a lot about K-limits in the first part, and I guess that was already a little bit technical, but let's get more technical. So let me just formally write down the definition of the K-limit, and let's see where this brings us. So we have a set A of Boolean strings, and we say that Y is the K-limit. Okay. For every subset of coordinates of size K, there exists as in A, which is they are the same on these coordinates. That definition here? Okay, good. Right. So let's also see for ourselves that this is something that has to do with the set being or not being computable by KCNS. Right, so let me just formulate the statement that suppose C.
And the K-limit be inside of the set?
Yes, it can be inside of the set, but like then it's not telling us anything, right? In fact, any string inside of the set is a K-limit, right? Because you can find a string in the set that coincides on every set of coordinates. So in that sense, yes, of course. Okay, suppose we have a KCNF such that it accepts set A. Then I want to say and y is a k-limit of A. And C should also accept y. Okay, this is very easy to see. I'll just draw some pictures of CNFs, I guess. So we have our clauses of with K. And suppose this is not true. Suppose our CNF rejects Y. Well, then some of the clauses should reject Y. Suppose it's this clause, right? So there are key variables here. X, I. The I with some signs here. Right. So key variables. And it rejects Y. Well, then there is also X. Let me call this set a variable I. There is X such that Xi is equal to Yi. X is A. Well, then this clause should also reject X, right? Well, then this is not true, so we reached a contradiction. Okay. Great. So if there is a k-limit outside of the set, then this set is not something that you can compute with k-CNF. You always get k-limits inside this CNF as well. But also, in some sense, the converse is true as well. I want to say that if there is no k-limit outside the set, then we can construct a k-CNF that accepts the set. Let me write this down. So we have our set A. And suppose there are no limits outside of A. And then a k-CNF such that it accepts A and it rejects everything else. Let's see that. Okay. So here's our Boolean cube. Here's a set. Let me construct this CNF, just adding clauses to it. Okay, let me pick any point here outside of it. I know it is not a k-limit. What does this mean? This means that there exists some set of k indices. So this is my y. There exists some set of k indices such that any point of A differs from y in these k indices. Okay, let me just add a clause to my CNF that says that we reject all points that coincide with y on these indices. And let me just do the same thing for every point outside of A. This is a k-CNF. So what is the size of this k-CNF? Well, maximum it will be something like 2 to the k log n, which is not that big actually. Because what are k-limits? This is a tool that helps you to prove a lower bound on circuit on the form to the k, because usually when you have a circuit, this is your last layer, you can restrict the fan in here in the last layer to be log of size. So when you're trying to prove 2 to the k lower bound, you usually deal with 1 in k here. So, okay, this is a little bit bigger.
This restriction, it's like a random restriction.
You can do this by random restriction, but you also can do this in a purely top-down way. I can tell you about this in a moment. Right. My point is that between corresponding lower bound and like upper bound that you get from the existence and non-existence of a k limit, there is a certain gap, which like it might matter, it might not, because logarithm is like it's not a very big function, right? So if you're proving some lower bound of sort to the n to the epsilon, you can always just like prove a lower bound to the n to the delta, or for any delta less than epsilon. But there are instances where this can matter actually. And let's go back to depth-free circuits again. Luckily, this is exactly depth-free. So I mentioned that best lower bounds that we have for depth-free circuits are of the form to the right? For parity, this is tight. There are circuits of size roughly 2 to the square root 10 that compute parity. For majority, we don't actually know. For majority, this is the lower bound. The upper bound that we know is 2 to the O of square root 1n. So that might be the crucial difference here between these square root and square root 1n. Because basically, we don't really have that many candidates of functions for which we should aspire to prove better than this lower bound. Majority can be one. Like, it wouldn't give us true exponential lower bounds, but as I mentioned, even reaching this just by a little would be already very nice, because this is like the extent of what we can do. And majority, I think, one of the few candidates that actually might be a little bit harder. So this is the place where it might matter. Okay. Right. Let me move to k-parity limits. So the analog of this is true for k-parity limits. Let me write this down. I can write just analogous statement here. C is k-parity CNF. C of A is 1. Y is a k-parity limit. Y is 1. And the proof would be more or less the same, right? Do I need to repeat it? Is this more or less clear? Yes, okay. Right, but when I try to do something like this, I can also formulate a lemma that looks somewhat like this, just replacing k limits with k parity limits and k CNFs with k parity CNFs. And I can just, again, do the same picture, add the k parity closest to my k parity CNF. The problem is that the size would be much bigger, right? Because how many parity like linear forms there are it's to the n, I believe, right? And you also need to do this to k power. So that's quite big. This is bigger than, like, significantly bigger than a lower bound that we aspire to prove. So this is why I had this question, like, is k parity limit complete? I can relax this somehow though, so that it would be complete in the same sense with, like, logarithm of difference. If I require a k limit with respect to not all linear forms, but okay, let's say that
Sorry, just to
Yes.
double check, K parity CNF is a conjunction of disjunctions of at most K parities, but
Yes,
with no bound on the parities.
yes,
Okay, good.
yes, exactly. Right. I can just relax a definition of k parity limit a little bit to get pretty much the same picture. Maybe I don't want to play against all linear forms. Maybe I want to play against a set of some predefined linear forms. I will explain what this means in a moment. Okay, suppose I am proving a lower bound of the form 2 to the n to the epsilon for some AC0 convulsive XOR circuit. If I'm proving this lower bound, then I have an upper bound on the number of parity statements that my circuit can use. Like, it's at most 6. It's not 2 to the n, it's less. So I can say, okay, I fixed some set of 2 to the n to the epsilon parities, and I only want to play against this set. And then, what do I get? So how many different, then I just need to replace t to the n here by t to the n to the epsilon, and we get something like epsilon times, where k is also like an n to the epsilon or something, so that would be something like this. So this is like much better picture than we had here. Is my point clear here?
And to the 2 epsilon.
And to the, yes, you're right. So not logarithm, of course, but something reasonable which we can still work with. So this means again that for lower bounds of this form, maybe I don't need a k parity limit that works for every kind of set of k parities that I can find. Maybe these k parity limits can be actually different points, but I should be able to find a point that works for this, for a fixed set of this set. Okay. Right. What's next in my plan? Okay. Let's talk about fan-in, this fan-in k of the circuit, that's the logarithm of the size. I'll just trace it out. So we're switching back to AC0 for a moment. Okay. Suppose I have a circuit of 2 to the n to the epsilon size. I can use a random restriction, for example, to make sure that this fan-in, just before the variables, is at most n to the epsilon. So that I can do with random restriction. We run into a little bit of a problem, though, when it's not just AC0, but AC0 parity gates, because we know that parity is very stable under restrictions. So we cannot reduce the fan-in here the usual way. But we can do this or something like this, appealing to K limits again. So this is the parity now. No, this is not parity. This is parity. That's the way. Okay. So when I'm implementing my top-down strategy, right here on this level, I need to be able to find K parity limit with respect to like some parities, some set, something. What can I do is I can find a lot of K limits. There actually should be a lot. Like this is a more robust notion than just finding one. There should be a lot. So I'm finding a lot. Let me just continue my descent, my top-down descent on the circuit, and okay. Let me pick the next step here, such that in this sub-circuit rejects the maximum number of K limits. Okay, so suppose I had the set S. This is my set of K limits. And this is the lower bound that I'm proving. So here I have at least S over 3 to the n to the epsilon K limits right here. Okay, if this is big enough, if this is like at least let's say again 2 to the n to the epsilon, then if this fan-in is too big, we cannot reject all this set, right? If this fan-in is bigger than m to the epsilon, then the zeros of this clause, it's the conjunction of more than m to the epsilon sequence. So like, if I'm looking at the zeros here, it is some linear system. Something. Well, if these are linearly independent, that's I guess is the important distinction. But in our model they are. Okay, I have some equations. There are n to the epsilon plus 1, for example, of them. And then the set that satisfies this linear equation is of size less than e to the n to the epsilon. So if we're able to find a lot of K limits, right, then we kind of get around the problem of reducing fan-in in this case. Because big fan-in cannot reject a lot of K limits. And for small fan-in, they fool the small fan-in. That's kind of the idea.
So you're not really getting rid of the large fan-ins, you're just actually dealing with them. You're saying that,
Yes.
okay, if they're, then they rule out the small set.
Yes.
Okay.
So here I'm picking the node here on my path that accepts a lot of K limits. Maybe in some other nodes, I could have large fan-in,
Right.
but I'm saying that this is inconsequential. I only care what happens here. Yes. So that's the idea. And then, okay, how much do? Great. Then let me tell you how to obtain a K limit. And then we can prove the lower bound for the mega slice. Let me define everything about unpredictability that we need. So suppose we have, again, the set X of some Boolean strings. And let me say that, okay. AI. is a certificate for the bit I if what this means is I'm looking at some bits in my string, and after I'm looking at this bit, I'm actually able to determine the value of some other bit. Let me give you an example. Suppose the set X only contains two strings, all zeros and all ones. Then, for example, if I look at the first bit of the string, this is actually a certificate for everything else. Like, I know that this is also zero, for example. In the same way, 2 and 1 is a certificate for everything else as well. Like, if I see that the second bit is 1, I can determine any other bit. Or let's take a look at another extreme example. Suppose X is the set of strings with even parities. Then, if I look at first and minus 1 bits, I'm able to determine the last one. Okay. So does this definition make sense? Okay, perfect. So this result, Peterson, says that if X has enough entropy or just is big enough, this is like good enough for purposes, and size of X greater than 2 to the n minus k, you can think of k as n to the epsilon again. Then probability that I is uniform random and X is uniform random. The probability that X contains a Q size certificate I is less than something like 1 minus QK over wait. No, minus QK over n. There are probably some constants here, but let's just forget about them. These are the parameters that matter. So, what does this mean? I'm taking some very large set, for example. So my entropy loss is n to the epsilon. Then, with high probability, when I'm taking a random string from this set and a random bit in the string, I wouldn't know what this bit is, even if I'm able to look at some other q bits in the string. So let me draw a picture. This is q, maybe like n to the epsilon. And here the I bit, and I have no idea what's there. And that's even if I'm allowed to pick this thing non-deterministically, right? This is saying that with high probability there is no certificate in the string for this bit. So this is actually something that will help us to generate k-limits. suppose that I is unpredictable in X. Then if I flip the bit, let me just denote this that I'm flipping the I bit. Is and well, let's just prove this.
Wait, what does I is unpredictable mean?
This means that X contains no. Okay. I omitted parameters here. Okay. Unpredictable or okay. These size certificates.
So K is your Q there,
Yes.
and the.
Okay. Let me denote this differently. So I can be in confusion. Yes. I think this is better. Great. Yes. If I is unpredictable in X for case size certificates, then if we flip the I bit, we'll get a K of it, or the set. Well, let's prove this. Again, I'm going to just draw some pictures. Here's my X. Here's my unpredictable bit. Let's say it's 0. Okay. Unpredictable bit. 2, 1, for example. This is X. This is X prime. Great. So I need to prove that for whatever set of indices I take here, I will be able to find something that looks the same in X. Well, if my set of indices doesn't touch this flip bit, this is easy. Oh, I had a nice chalk. Okay, so example, this is my set I. Okay, thanks. Then here we have the same thing. Okay, great. Now, what if my set I actually touches this bit, right? We cannot just take X to be the thing, but I'm saying that, okay, let's suppose that this is actually the set that distinguishes X prime from everything else. So what if it's not a K-limit and this is the witness to it? Okay. Well, then this in here would be a certificate. Because what if we look at this string and we don't have anything in a big set of X that looks like this? Maybe I'll use, I don't know, some numbers here. We don't have anything that looks like this. Well, then this should be the certificate that this bit is 0. Because we have that string here, like if this is here, then we have 0 here. If we don't have 1, this certifies that this is necessarily 0. Okay. So this is the way to generate a K-limit of a set. And moreover, to generate them in mass, right? Because this is a probabilistic statement. You you can take random x from the set, and you will get basically you get a k-limit for every unpredictable flip. And this says that there are a lot of them. Okay. We are ready to prove a lower bound for middle slice in this or composed with CNF basis model. Okay. Let me omit the specific exponent here. It's 2 to the m to the epsilon. Or right. Let's prove it. This is the middle slice. And this is the circuit. Or and or XOR variables. Okay. Let me do the first step down the circuit. This corresponds to picking the subset of one input. What I will do is I will pick the subcircuit that accepts the largest chunk of the middle slice. Here it is. The middle slice itself is of size roughly to the n of the square root 10. And this is circuit of size to the n to the epsilon. So let's just say that this chunk is roughly 2 to the n minus n to the epsilon. There is like also some square root 10 here, but let's just hide it here somewhere. It doesn't really matter. Okay, I have this quite a big chunk of a Boolean cube. And now I'm here in this subcircuit where we already fixed the affine transformation that we're applying. So it is some matrix A, which is just the change of coordinates. So basically, I feed my inputs here, I apply the affine transformation, and then something else happened. So just like the AC0 part here, what it actually computes after the change of coordinates, it's something else. It doesn't look like this. So here's another drawing of my Boolean cube. There was the middle slice, not somewhere. This is the chunk that I chose. Maybe yes. Middle slice, chunk of the middle slice, and the rest is my zero input. Okay. So what I need to do now is I need to find a k-limit in the new coordinates for this set, the chunk of the middle slice that mapped somewhere. And I need to make sure that this k-limit is outside of the middle slice itself. Okay, I erased these pictures here, but you might have noticed that when we flipped the unpredictable bit, we didn't actually say that the string that we're going to get is not in the set, that this is something outside. This is something function specific that you need to prove for a particular function. Because like this part, it just uses the largeness of the set. Okay. So, so I have my input X, the original input X. I have a matrix A. That is a change of coordinates. And I get some vector from here. Y, right? Let me apply to this set my unpredictability statement. So I'm taking a random input here, and I'm flipping the bit in these new coordinates. So I'm flipping the bit. And this corresponds, like I can just apply the transformation the other way around. And I can say that I'm flipping this bit, it corresponds to me flipping some bits in X. I don't know which, but like it's some vector that I get by multiplying A prime by the basis vector, where y equals X. Okay. So if after flipping, I get a point in here, I'm good. I found the k-value. The bad situation is where I'm flipping the point, I'm flipping the bit, and I end up back in the set, or maybe even here, just like in the middle slice here. That's like the bad situation that we want to avoid. We want to prove that there is no affine transformation that would have gotten rid of all k limits outside of the set. Like there is no change of coordinates such that they're all here. Great. Okay, what does this correspond to in the original picture? Like here, we're flipping a bit and we're back in the set. How does this look in the original picture? Well, we're also flipping some vector, and we are back in the middle slice. But what does this mean actually? So suppose, forget even for a moment about the probabilistic side of things here. Let me say that for every vector here and for every bit flip, I'm just ending back in the set. Okay. This means that all these flips land me back in the middle slice. These are linearly independent vectors because A was just full rank affine transformation. So all of these things, they are linearly independent. So in particular, there's another observation is that if this bit flip lands me back in the middle slice, that means I preserve my Hamming weight with this flip. Let me draw this a little bit. So here's my X from the middle slice. Here are the bits that get flipped. This flip preserves Hamming weight, and in particular, the sum in these bits is of even parity. Is that claim okay with you? Yes. So we have that for like this second. If any flip for any x lands us back in the middle slice, we have this for every I and for every x. So in particular, we have some non-trivial linear form outputting 0 on every one of our vectors. And we have n of these independent linear forms. And so on. So this would contradict the largeness of the set immediately. Like if you have this linear system of quite a lot of equations, like n equations, there's no way that so many points could correspond to these equations, right? I cheated a little bit here. I said that for every point and for every bit flip, we get back in the middle slice. But this is easily scalable to use what we actually have, the probabilistic statement. I'm just saying, okay, for most the points, for most of the bit flips, I land back in the middle slice. And then I still have that I have a very high correlation with some affine subspace of very large codimension. So that's kind of the idea. I don't want to write down all the calculations, but is the idea clear? Basically, it just means that middle slice cannot have such a correlation with the with affine subspaces. Yes. Okay. So we have. Okay, I'm almost out of time, I think. So let's talk about the open questions once again. Because as you can see here, this procedure that helps us to produce a K-limit it is a very local change. I'm changing one bit in my string. Or here I'm changing one bit in my string in some other coordinates, which I suppose is still somewhat local. But here's the example where this might be not enough, actually. What can I erase? Maybe this one. Okay, so from Bazi, Razborov, and Braverman, we know that it is hard for AC0 circuits to distinguish two k-wise independent sets, for example, or to distinguish a k-wise independent set from a uniform distribution on the Boolean cube. So, okay. I have my Boolean cube. I have my maybe square root k-wise independent sets. They are disjoint. It's hard to separate these sets in AC0. But here's the thing, the size of the set can be quite small, right? We can get a square root n-wise independent set of the size, I think, something like this should be the right bound. And for example, here, largeness of the set is a very big thing. Like here you have a very big entropy loss comparing to the Boolean cube. So you cannot apply this thing. And also, it is not super clear to me how sparse can these things be. But I would guess that they can be pretty sparse. So my point is, you need to get from very small set, from a very small set by some modifications. They shouldn't be so local as they are here. And moreover, here's like a very, maybe even a toy version of the problem that still encapsulates the difficulties of how do we find the K-limit from. Suppose we have half of a k-wise independent set, square root n-wise independent set. Then again, by all the circuit lower bounds that we already know, we actually know that half of the Boolean cube should be k-limits. Like it's just hard to separate this set from the rest of the Boolean cube within AC0. So if you take half of such set, then even a random point in the Boolean cube should be a k-limit with very high probability. Can we prove this? I think it's like a very interesting question that kind of shows the difficulties in finding k-limits are. regarding this locality and size, one could also look at the situation where in the first step, we separate, for example, L1 inputs to sets that are linear codes, for example. You can probably get such covering by just shifting the linear code. So then we would guarantee that these things are kind of apart, like different points in the set are very apart from each other. So that's also not a very local thing. You would need to do something globally to find a element. Right. Okay. Do I have any more time? I think that might be it.
I have a few minutes to wrap up if you like.
No, I think it's a good place to stop. I was thinking also to tell you about the motivation for studying this that comes from the mod 6 perspective, but I think it needs quite a little bit more time to explain things. So I think it's a good place to wrap up this.
Okay, thank you.
Specify the question about the k-limits again.
Which one? They're all about k-limits.
The old one.
This one? Okay, so here's the very simple version. You have square root n wise independent set, right? Prove that a random point in the Boolean cube will be a k-limit with high probability without appealing to any kind of polynomial approximation.
Why does the question have anything to do with approximation?
Well, because we know that it's true because of polynomial approximation. We actually know that half of the Boolean cube will be k-limits for this half of the square root n wise independent set. This just follows from the existing circuit lower bounds.
And what is k here? What is k here?
You can think it's square root n or any small polynomial you like, n to the epsilon, whatever you like.
Do you want a more like combinatorial proof or?
You mean about square root n wise independent set? Yes, yes. But also I think it's like this example is highlighting what is wrong right now with the way we're finding k-limits.
Would you mind explaining to me why circuit lower bound implied this result?
Sure. Okay. So we know that it is hard for AC0 to separate, to like distinguish a square root n wise independent distribution from just a uniform distribution in the Boolean cube. Right? So we can take a look at just that's not the picture I want to draw. A depth-free circuit. We know that in particular it's hard for depth-free circuits. Okay. Here's a usual picture of depth-free circuit. In fact, let's take depth-2 circuit, right? And let me say that I want to say that the circuit cannot do this with the error 1/2 or whatever. Okay. I need to be careful what are my is this or and, but like we'll get to this in a moment, I think. So if I'm saying that this circuit computes actually this with the error 1/2, what I need to do is I need to remove half of my square root n wise independent set. Okay, I think this should be and then. I know that after this, a circuit of small size cannot actually compute this. Ones here and zeros on the rest of the cube, and I'm not counting this half of the area. Okay. Right. This means that there should be k-limit here. And in fact, we also know, thanks to the circuit lower bounds, that that are like average case, right? That if AC0 circuit accepts roughly a half of the set, it should also accept roughly half of the Boolean cube. This is something from this Riazanov sort of paper, one of these or all of these.
That's the meaning of indistinguishability.
Hmm?
I mean, what is that is the meaning of indistinguishability of the two distributions?
This means that I suppose that the probability that you output one when you feed one of them is like one thing.
Within epsilon,
Huh?
within epsilon distance.
Yes.
accepting.
Yes, yes, pretty much like this. Is that okay? Okay.
Okay. Thanks again.
Yeah.